Hello, what follows is a summary of some of the horizontal transformations, including horizontal compression and stretch, along with horizontal shift. We're going to look at how to go from the equation to the graph and back again. Basically, we're just going to reverse the same techniques. So when analyzing y equals square root of 2x minus 5, before we do anything, we need to rewrite or rearrange the way the function is written. By factoring out the 2 from 2x minus 5, we get 2 times the quantity, x minus 2.5. This enables us to identify the horizontal compression, but this time we'll be compressed after the graph is shifted to the right 2.5. In other words, the square root graph is going to look something like my little mental sketch here. So for starters, I find the origin shifted over 2.5, and typically I would go over 1, up 1 to find the next point on the square root graph, but this time I need to go up 1 over a half. So from 2.5 over to 3, that should be a point at 3, 1. There's also going to be a point, instead of going over 4 up 2, I'm going to compress that and go over 2 up 2, giving me my second point, which enables me to draw the square root graph as shown. Checking to verify the 4.5, 2 is indeed on the graph, I find that there's a solution to the equation, and therefore I have it correct. But just to be sure, I put the equation into Desmos to see if I get the same graph, and indeed I do. Now in this case, we're going to focus our attention on this graph, which appears to be a horizontally compressed, shifted square root graph. What I need to do is take on some clues from the orientation of the graph, particularly the starting point and the first point along the curve. So for the starting point, I'm going to recognize, or actually for the first point along the curve, that my A value is going to be 2 in terms of horizontal compression language. That is to say, if I went up 1 and over a half, that means my A value is going to be 2. I also went left 2.5, and therefore all I have to do is show the 2 and the shift 2.5, and then the last thing I do is distribute the 2 and get the final form of the function shown. This is the same function from the previous slide. Just to verify, the point 7.3 was given, so I'm going to verify that 7.3 is a solution to the equation that I wrote. Now looking at the second function, it's an absolute value graph. It's going to be compressed and shifted to the left. But again, I rewrite the function to determine that we will horizontally compress by a factor of 3 and shift to the left 3, not 9, to get a graph that looks something like that. So the first thing I'm going to do is move the graph of the vertex of the graph over 3, and instead of going up 1 over 1, I'm going to go up 1 over 1/3. And I can do the same thing by going over 1 up 3 because that's the slope of this line. Using slope to plot many points is something that you can do with absolute value graph, because as you recall, absolute value graphs are just two lines with opposite slopes. So that's why I put in the other point symmetrically, and I'm going to put another point if I wanted to draw the two lines, or rays. Label a few points and check, and everything's cool. Alright, and then that's another checkpoint right there, and I checked it also on Desmos. If we were given the graph, we could visualize this as a vertical stretch or a horizontal compression, but based on the given point, we're going to work from the horizontal compression standpoint. So to figure out my A value, after I determine I went left 3, I'll determine my A value by going up 1, and I see that I go over 1/3, which means my A value is going to be 3. So writing my equation, 3 times the quantity, x plus 3, distributing the 3 to get 3x plus 9 absolute value. That is, we're going to take, once again, we're going to take our given point, negative 4, 3, and verify that it indeed is a solution to the equation, and it is. So these two functions, just another examples to demonstrate how we can take multiple stretches, shifts, and compressions. And in this case, we are going to look at all the stretching from a vertical standpoint. So we're going to go over 1 from wherever our vertex is relocated. We're going to go over 1 up to the graph, and that's going to tell us our A value. So this is the format we're going to be using. In my graph, I recognize that the vertex has been shifted to the right 1, up 3 to get my new vertex. I identify my A value as 2 because it's vertically stretched by a factor of 2. That produces the following. Notice the color coding. Check this with Desmos to verify that it gives you the exact same graph. And down at the bottom, once again, I determined a shift to the left of 2. And to do that, I had to draw in my asymptotes so I could really clearly see. Oops, didn't mean to do that. And I can't even undo it. Anyway, what I was trying to say was that we can draw the asymptotes, this dotted line here, and draw that dotted line there, and that shows you where the new vertex is going to be located. And I can see I shifted left 2, down 3, and the A value is 3. I would have gone over 1, up 3, but I was getting cluttered with all my drawing. So since this graph is symmetrical, I can find the A value in 2 different ways. Transforming y equals 1 over x, multiply by 3, shift to the right 2, and shift down 3, and I end up with this simplified form of an equation. And again, we can verify with technology. Finally, on this particular video, just going to review graphing two functions using transformations in general, and following the whole format. So in this case, I'm going to see a vertical shift up 1, I'm going to see a flip over the x-axis, and I'm going to see a vertical compression. And that's all going to happen in reverse order. So we're going to vertically compress, flip over the x-axis, and shift everything up 1. All the solutions to the graph will fall on that. That's going to make a graph that looks something like that. So once again, I start by finding the shifting up 1. And normally I would go over 1, up 1 to find the next point on my graph, but this time I'm going to go over 1, down 1/8. So I'm actually going really small incremental. So I'm going to also use the fact that if I go over 2, normally I would go up 8. Now I'm going to go over 2 and down 2. That's an or down 1, sorry, over 2, down 1, because that's an 1/8 of 8. So instead of over 2, up 8, I go over 2, down 1/8 of 8, and that gives me that second point. The other 2 points are found using symmetry, and I create a cubed-looking graph over those 3 points. I'm making a point to show this and this. These are the 2 points that show the very first effects of the compression of 1/8. So, check that with calculators and with substituting points in. For the square root function, once again, I'm going to factor out 1/4, which is kind of funny looking, but when I factor out the quarter, it actually makes 2 bigger, because 1/4 times 8 equals 2. So now we can see a shift left 8, horizontal stretch by a factor of 4, and a shift down 2. It's going to make a graph that looks something like that. It's really, really horizontally stretched out. So to begin, I go to the left 4 and down 2 to get my starting point. And from there, I need to go, usually I would go up 1 over 1, but this time I'm going to go up 1 over 4. And sorry, notice by the way I did count by 2's here, so that's over 4. And then normally I would go up 2 over 4, but now I'm going to go up 2 over 16. 4 times 4 is 16. So my next point is actually going to be here at 8, 0. Creating this square-rooty looking graph. And again, I check this with technology. Oh, and I could also put in a point. So you can see down here, I check my answer, putting in x equals -2, and I should get 2 as a result. Here I check with x equals -4, I should get -1 as a result, and indeed I do. Thanks for watching.